Hello everyone. In this lecture, I will be discussing JK flip-flop and T flip-flop. The JK flip-flop can be constructed from SR flip-flop with additional circuitry. In SR flip-flop, for the input S equal to 1 and R equal to 1, so the output it is an invalid state. So to overcome that problem, here in JK flip-flop, the output Q and Q bar is connected back to the input of the NAND gate. On this connection, it avoids the invalid state in the JK flip-flop. The logic symbol for the JK flip-flop is shown here. Consider J equal to 0 and K equal to 0. When one of the input of the NAND gate it is equal to 0, the output of the NAND gate will be equal to 1. So S bar it is 1 and R bar equal to 1. So this means S equal to 0 and R equal to 0. So in the SR flip-flop with S equal to 0 and R equal to 0, the output it is no change. So for the J and K input equal to 0, the present state is same as that of the previous state, which indicates no change. So coming to the next case, for J equal to 0 and K equal to 1. So here I am assuming that the previous output are Q is equal to 1 and Q bar equal to 0. So this output is fed back to the input. So for the first NAND gate with the J equal to 0 and here the other input 0 and clock will be rising it, that is it is indicating it as 1, right? So with this condition the output of the NAND gate will be equal to 1. In the lower NAND gate with K equal to 1, the other input equal to 1, the output it is equal to 0. So S bar it is 1, so S equal to 0 and R bar it is 0, so R equal to 1. So for SR flip-flop with S equal to 0 and R equal to 1, the output it is in reset condition. So that Q it is equal to 0 and Q bar equal to 1. For J equal to 0 and K equal to 1, the output Q equal to 0, it is in the reset condition. Next case, for the input J equal to 1 and K equal to 0. Let us assume that the previous output as Q equal to 0 and Q bar equal to 1. So these output are fed back to the input of the NAND gate. So the upper NAND gate with both of the input it is equal to 1, the output it is equal to 0. And the lower NAND gate with the input 0, the output it is equal to 1. So with S bar 0 implies S equal to 1 and R bar equal to 1 implies R equal to 0. So in SR flip-flop with S equal to 1 and R equal to 0, it represents the set condition, that is the output Q equal to 1 and Q bar it is equal to 0. So for J equal to 1 and K equal to 0, the output Q equal to 1 representing the set condition. So coming to the next case with J equal to 1 and K equal to 1. So let us assume that the previous output as Q equal to 1 and Q bar equal to 0. With the output fed back to the input, the output of the first NAND gate will be equal to 1 and the output of the lower NAND gate will be equal to 0. So for S bar equal to 1, S equal to 0 and R bar equal to 0 implies R equal to 1. So for this condition for S equal to 0 and R equal to 1, the output is Q equal to 0 and Q bar equal to 1. If I assume the previous output as Q equal to 0 and Q bar equal to 1, I will be getting here Q will be 0, so now the new output will be equal to 1. And the older value Q bar it is 1 and new value will be equal to 0. So for J equal to 1 and K equal to 1, the output are complement of the previous output. So it represents the toggle condition. I can assume the previous output as either Q equal to 0 or Q equal to 1. If you go with any of the case, the output will be the complement of the previous output. So characteristic table, it represents the operation of the flip-flop in the tabular form. Right? So again I am considered the positive edge triggered flip-flop. So for negative edge and for the logic 0 or logic 1, irrespective of the J and K input, the output Qn plus 1 will be equal to Qn. That is, there will be no change in the circuit. And for positive edge, for J equal to 0 and K equal to 0, Qn plus 1 equal to Qn, no change condition. For J equal to 0 and K equal to 1, Qn plus 1, 0. For J equal to 1 and K equal to 0, Qn plus 1 equal to 1. And for J equal to 1 and K equal to 1, Qn plus 1 is equal to Qn bar. So it represents the toggle condition. So now representing using the waveforms, for the J and K input given, we'll draw the output Q. Right? So at the rising edge of the clock, J it is equal to 1 and K equal to 1. Right? So when J equal to 1 and K equal to 1, the output Qn plus 1 is a complement of the previous value. So the previous value is 1. So now the output it is complement, so it is 0. And for next case, for the next rising edge, with J equal to 1 and K equal to 0, the output it is 1. And for the next rising edge, with J equal to 1 and K equal to 1, the output it is toggled. Right? So previously it was 1. So now it is equal to 0. Similarly, all the other cases. Now I am going to derive the characteristic equation from the characteristic table. So this characteristic table, it consists of the present state as well as the flip-flop input. And from the Qn plus 1 values, I can plot the K map. So now group the values of ones. I will be getting the first grouping, this it is equal to J Qn bar plus, and this second grouping it is equal to K bar Qn. So this is the characteristic equation of the JK flip-flop. Qn represents the present state and Qn plus 1 represents the next state. So coming to the excitation table, this excitation table, it lists the input required for the given change of state. So it can be derived from the characteristic table. So for the first case, when Qn equal to 0 and Qn plus 1 equal to 0, so from the table I can see that J equal to 0 and K it can be either 0 or 1. So K it is don't care. And for Qn 0 and Qn plus 1, from the characteristic table I can write J it is equal to 1 and K it is either 0 or 1. So K it is don't care. And for the next case, when Qn equal to 1 and Qn plus 1 equal to 0, J it is either 0 or 1. So it is J it is don't care and K it is equal to 1. And for the last case, for Qn equal to 1 and Qn plus 1 equal to 1, J it is either 0 or 1. So J it is don't care and K it is equal to 0. So this is a characteristic table and the corresponding excitation table of the JK flip-flop. So next, coming to the next type of flip-flop, T flip-flop. This flip-flop is constructed from the JK flip-flop by connecting the input J and K together. So connecting J and K together and then giving it as a T input, we'll be getting T flip-flop. So this is a logic symbol. In this diagram, it represents the logic diagram for the T flip-flop. So characteristic table, again it is a positive edge triggered flip-flop. So for negative edge triggered or for logic 0 or logic 1, irrespective of the input, the output it is same as the previous value and there will be no change in the circuit output. And for the rising edge of the clock with the toggle input T equal to 0. So with T equal to 0, it means J it is equal to 0 and K it is equal to 0. So with that condition, the output Qn plus 1, it is equal to Qn. It is indicating no change. And for t equal to 1, it indicates j equal to 1 and k equal to 1. So the output Qn plus 1, it is equal to Qn bar. So it represents the toggle condition. So now representing using the waveforms, and the input it is t. For the rising edge of the clock, if t equal to 0, the output it is same as the previous value. So previous value it is 0. So at the rising edge of the clock, it is again 0. And for the next rising edge, the t it is equal to 1. So with t equal to 1, the output q, it is the complement of the previous value. So here in the second rising edge, the output previously it was 0. So now it is equal to 1. And for the third rising edge, toggle t equal to 0. So it means there is no change. So here the previous value is retained. So this is the timing diagram for the t flip-flop. Next, coming to the characteristic equation. So again, draw the characteristic table and then mark the values of Qn plus 1 in the corner of map and then group the corresponding ones. In this, there is no groups, so there are two isolated ones. So correspondingly, the terms are, the first one, it corresponds to t Qn bar, and the second term, it corresponds to t bar Qn. So the output Qn plus 1, it is t XR Qn. So this is the characteristic equation of the T flip-flop. So next, coming to the excitation table. So this excitation table is derived from the characteristic table. So for the consider the first case with Qn equal to 0 and Qn plus 1 equal to 0. This corresponds to T equal to 0. And for second case, when Qn equal to 0 and Qn plus 1 equal to 1, it corresponds to T equal to 1. Next, for Qn equal to 1 and Qn plus 1 equal to 0, it corresponds to T equal to 1. And for the last case, for Qn equal to 1 and Qn plus 1 equal to 1, it corresponds to T equal to 0. So if I observe here in this table, when the toggle input is 0, the next state and the present state, it is same. It is no change, right? And for the toggle input, it is equal to 1. The next state, it is a complement of the present state. Thank you. Happy learning.